So now we're going to tackle this problem that we've been building up to, which is writing down some integral or a Fourier transform that will calculate the propagation of a wave in the presence of dispersion. So we have some wave shaped in space, so it's a function of x at time equal to 0, and that'll have this Fourier transform over k. Now we can write f of x naught as an inverse Fourier transform over k. And I'm going to write this inverse transform out explicitly so we can see where all the phase terms interact with each other. To find the shape of the wave in space at some later time t, we need to rotate all of these phase terms here with the correct phase, and the correct phase is given by the frequency omega. So we add the phase rotation term e to the negative I omega t into our integral, and so each of these terms here is being rotated by some phase that depends on omega. Well, what is omega? In the case where we have no dispersion, omega is directly proportional to k, and the constant of proportionality is the speed of the wave c. Substituting this in, we get this integral here, and we can look at this and go, well, that's actually just a phase rotation that is linear in k, and we can use the shift theorem to immediately write down the shifted waveform. And so we can see that the waveform, the initial waveform, f of x naught, is just being shifted along the x-axis at the speed c. Now the notation here is a little clunky because I'm expecting some function of x and t, and here I do have a function of x and t, but the dependence on time is trivial and just pops up in the x part here and is just shifting it along in space. And so I've left this one as 0, so apologies for this kind of weird notation here. What this is saying is that the initial waveform does not change shape and it's just shifting along the x-axis at the speed c. When we get to something that has dispersion, we can't do it like that. So we're going to write omega as a function of k, and this is a now more complicated function of k rather than this sort of trivial example here. So we can write out our function of x, f of x and t, as this inverse Fourier transform, where now the phase shift here will depend on omega, but omega is a function of k, and that depends on the physics of the situation. And we can rewrite this using our inverse Fourier transform notation as the inverse Fourier transform of the initial wave, or in Fourier space, multiplied by the phase terms here, omega is a function of k. And this single transform here gives a new function of space at a single later point in time. So if you're given a function of space, you can calculate what it will look like at some later time t. We can repeat exactly the same sort of derivation or calculation over time instead of space. So imagine now we have a wave passing a single point in space, and it goes past that point in space with some function of time. And then it'll have a Fourier transform over omega. And we're doing this at, say, x equal to 0. So now we can write down our function of time in terms of its Fourier components in omega instead of k. And to find the shape of the wave at some point in space, then we must rotate each omega with the correct phase, and the phase will depend on k. So we add the phase rotation here in terms of k. Again, if we have dispersion-free waves, then k is proportional to omega, with the constant of proportionality here being 1 on c. And so we can write down our function of x and t as this Fourier integral here, recognizing again that this is easily done with a shift theorem, so that now our initial function of time, f of naught t, can be just shifted along in time using this constant here, x on c. So it's exactly analogous to the previous derivation. We just reverse the roles of x and t. So with dispersion, same sort of thing. We write k as a function of omega, and we get this kind of integral here. So we have an inverse Fourier transform that gives a function of time for a single point in space x. So if you have a function of time at x equal to 0, you want to see what it looks like at some later point in space, this is the kind of transform that you do. Before finishing this topic, I just want to say something about the symmetry that we can identify in the dispersion relation. So here is our function of x and t. It's calculated from some initial position of the wave and then propagate it over time using this phase factor here. Now, we know that f of x and t must be real. That's because waves don't have imaginary amplitudes. So for a real function g of x, we have this symmetry relation in Fourier space. If we take this as g of k, that means that the conjugate of this whole thing here, which is equal to this, must also be equal to this expression here where I've just changed k to negative k. But we also know that this is true for the initial Fourier transform of the wave because that's real. And so the upshot of this is that the dispersion relation omega as a function of negative k must be equal to negative omega of k. That's a consequence of just following this math through. And so because f of x is real, the dispersion relation must be an odd function of k or omega. So I've done it here as omega as a function of k, but if you did the derivation with k as a function of omega, you get the same result, obviously. Now that's kind of neat. There's a lot more one can say about the properties of the dispersion relation, and causality actually puts really firm constraints on what a dispersion relation is allowed to look like, and this comes in the form of the Kramers-Kronig relations. Now, there's some details of how this works on chapter 16 of STEC if you're interested. It's beyond the scope of this course, but if you do advanced electromag, so that's Phys 3102, then Kramers-Kronig will be explored in more detail.